Up where we left off. So in that last video, I went through this one learning goal right here. So know the basic shapes and radial probability distribution graphs of the s, p, d, and f orbitals. So more importantly, s and p, those are going to be the emphasis. And know how to compute total nodes, radial nodes, and angular nodes. Okay. So that's what we went through that last goal. That's what that last lecture. This is what I want you to get out of it. Okay. So now we're going to go through these orbital energy level diagrams, how to populate with electrons, and how to come up with a new concept I'm going to introduce called the electron configuration. Okay, so you can see I've got the periodic table here in front of me instead of a calculator. So we're going to be really living and breathing by this periodic table here. Okay, so recall. So last time I described that because of all of this electron interference and electron, what we'll later call shielding, the levels split. Okay, so 2s and 2p are only the same for hydrogen, but not for anything else. 2s and 2p levels split for any other electron. Okay, and so the order of levels gets really complicated. And as we're also going to see, there are exceptions, which I'm not going to worry too much about the exceptions. There are a few exceptions that I do want you to know. Okay, but we don't have to memorize this as long as we can read it off the periodic table, right? So starting at hydrogen and helium, that's 1s. And then the next level, lithium and beryllium, 2s. And then if I keep going across, boron through neon is 2p. Okay, and then moving along, 3s. And then 3p. And then 4s. And then now 3d, 4p, 5s, 4d, 5p, 5s, and then after 5s, 4f. And then now after 4f, 3, 4, 5d, then 6p, then 6s, then 5f, and then finally 3, 4, 5, then 6d. Okay, so the slide that you want to study from to get those orders is this slide right here. Okay, that's giving me those correct orders. If I start from the top left corner, left to right, top to bottom. So left to right and then move down one, then left to right and then move down one, then left to right. Okay, so let's go through it. We're going to go through many examples here. Okay, so let's start with hydrogen. And so what I'm also going to do is introduce something called electron configuration, which is a type of notation that we use to summarize this diagram. Okay, so hydrogen on the periodic table, there it is. It only has one single electron. Okay, and I put that electron into this orbital by drawing an arrow pointing up. I could have drawn an arrow pointing down. Remember, that's plus 1/2, minus 1/2. We don't know which one it is. Okay, but because there's only one in there, that's the only one that I put in. And then look, based on this, my electron configuration, I write it as 1s1. So 1s1 is the address of hydrogen on the periodic table. Okay, 1s1, there it is. All right. So what about helium? Well, helium's next, right? One more over. Okay, so helium has 2 electrons. So how do I populate them in this diagram? Well, I go 1, 2, and now that makes an electron pair. This is why helium is a noble gas, because as it turns out, paired up electrons are really stable. We will see that's what the noble gases have in common. They have all paired up electrons. Okay, and so now the electron configuration for helium would be 1s2. The 2 means 2 electrons in the 1s orbital. This is helium's address, 1s2. Okay, and so I'm just going to keep going through examples, and all we do is just keep populating them Based off the Aufbau principle, electrons are added one at a time to each successive orbital in order of energy. Okay? So we did hydrogen 1s1, we did helium 1s2. So as you can see, what's going to come next, lithium, 3 electrons, 1, 2, 3, okay? And so I'd do it by saying 1, 2, 3. We only pair up the electrons if we have to. Because after all, they are electrons, they're negatively charged. They do want to repel each other somewhat, okay? So now this address, or this electron configuration, becomes 1s2, 2s1, okay? There's another shortcut that I could also say, all right? And because, for example, I know helium is 1s2, when we write helium in a block like that, that's the same thing as saying 1s2. So I could write lithium's electron configuration as helium bracket 2s1, okay? Either or works. So when you say the complete electron configuration, that usually means this, 1s2, 2s1. But we can use it's called the noble gas shorthand notation. And we can replace a noble gas configuration with that noble gas symbol. As you can see, for helium, it doesn't really do much for us because it's just as easy to write 1s2 as it is to write helium. But as we get into the heavier elements, like iron or rubidium or something like that, this noble gas configuration becomes a lot more useful, as you will see. Okay. So now what about beryllium? 4 electrons. 1, 2, 3, 4. There's beryllium. Okay. So I'm going to go 1, 2, 3. And now where do I put it? Well, you notice that beryllium is still in this 2s block, right? So it gets paired up in the 2s. And I could write this configuration as 1s2, 2s2, or I could write this configuration as helium 2s2. Okay? That works. Let's keep going. Okay? And as you can see now, what I've done instead of going through all of those one by one, which I could, right? If I were to go to boron next, then boron is going to have a p electron. Okay? So here I'm showing the diagram for you just slightly different, only showing you the 1s, 2s, and 2p. Okay? So, but now as you can see what happens, right? Lithium and beryllium, we did those examples, 1s2, 2s2, which I could also write as helium 2s2. But now look what happens with boron. Boron, we get 1 extra electron, so we place it in that first 2p block. Okay? And now that becomes 1s2, 2s2, 2p1. Or I could write it as helium 2s2, 2p1. But now look what happens with carbon. Okay? So I'm adding 1 more electron, but I don't pair it up because there's open orbitals. And if there are open orbitals, those electrons will spread in. Much like how you all are in the lecture hall, if there's an open seat, you will take it, right? I know this. I've been teaching college for 10 years now. If there's a seat next to a person, but then there's also an open seat, you're going to take the open seat. I know this. You're not going to take the seat next to the person unless you really like that person and you're trying to date them or something. So the electrons will fill into the open spots, right? So carbon becomes 1s2, 2s2, 2p2, or helium 2s2, 2p2. Okay? And now you can see we go one at a time. So nitrogen becomes 2p3. Oxygen, now we have no choice, but we have to pair it up. So that becomes 2p4. Fluorine becomes 2p5. And then now finally, neon has a full shell. So I'm going to write that as full shell. 1s2, 2s2, 2p6, all that is filled. That's what makes it a noble gas. So as it turns out, having a full shell really stabilizes an atom. And now we can adopt a new nomenclature, right? So I can write 1s2, 2s2, 2p6 as just simply neon. So now once I go past neon, I could keep writing 1s2, 2s2, 2p6, and then keep going it. Or I could just abbreviate any 1s2, 2s2, 2p6 as just neon. And that becomes much easier to write. Okay? So now let's keep moving forward. Let's do sodium. So we know that sodium, right, we filled it up to neon. We know neon is 1s2, 2s2, 2p6. So let's do that. Here's my 1s2. Here's my 2s2. Here's my 2p6. And notice I still put them in one at a time. Okay. So all of that right there, sodium with 11 electrons, I could write as 1s2, 2s2, 2p6, or I could just simply write that as neon. But now I've got 11 electrons, right? That one extra electron is a 1, 2, 3s electron, right? That's the next level. So there it is, okay? So 1s2, 2s2, 2p6, 3s1, or just simply neon 3s1. Okay, so now I'm going to divert from filling out the rest of the atoms, and we're going to talk about a really interesting phenomenon. Why are group 1 elements always +1 when ionized? Right, so think back to this. We know that hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, they're always +1 when ionized. Why? Well, let's do the electron configuration. So we know sodium, so sodium solid is 11 electrons. But sodium plus has to have 10 electrons, right? When we make a cation out of it, we remove one single electron. So let's populate 10 electrons on this thing. It's going to go 1s2, 2s2. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay? So the electron configuration of sodium plus is the same as neon. We call this isoelectronic. Iso means the same. So sodium plus has the same electron configuration as neon, the noble gas. And if we were to do that example for potassium, okay, let's follow this. Potassium plus is the same as argon. Rubidium 1 plus is the same as krypton. Cesium 1 plus is the same as xenon, and so forth. So all of these elements are always +1 because that gives them the stable noble gas configuration. So sodium loves being sodium plus. And if I relate this to our discussion of potential energy, right? Go back to the thermodynamics. Sodium as a metal has a ton of potential energy to become sodium plus. It really, really wants to become sodium plus because it will have the stable electron configuration of neon. So sodium as a metal just has a ton of potential energy. So when sodium goes through this reaction where it releases an electron, that's very exothermic. And so if you've ever seen somebody throw a chunk of sodium into some water, it explodes and releases a ton of energy because sodium is having an electron released to give it that stable noble gas configuration. Okay? So the group 1 elements as solids just have an enormous amount of potential energy to become +1 ions. They really want to become +1 ions. That's why we observe them all as +1 ions in nature. All right? Whew, oh, excuse me. Okay, moving forward. So now what about the halogens? What about fluorine? Okay, so here's fluorine. So let's do its configuration. So it has 9 electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so that's 1s2, 2s2, 2p5. So now why are halogens always -1 when ionized? Well, look, now we've got 10 electrons, and maybe you can guess where this is going, right? There's fluoride, F minus, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So also fluoride is isoelectronic with neon. And now if we notice here, right, look, fluoride becomes isoelectronic with neon, chloride becomes isoelectronic with argon, bromide to krypton, iodide to xenon. So just like in the previous example, the halogens always are -1 because that gives them noble gas configuration. Well, what about oxygen? Why is oxygen always -2? Well, look, oxygen's always -2 because if it gains 1, 2 electrons, it also becomes isoelectronic with neon. Well, what about nitrogen? Why is nitrogen always -3? Once again, because 1, 2, 3, it becomes isoelectronic with neon. So all of those trends, all of those charges that I made you memorize back in the beginning, like why is aluminum always 3+? Well, aluminum's always 3+ because now when I go positive, I go backwards, right? So aluminum is always 3+ because now I go 1, 2, 3. Okay? Why is zinc always 2+? Well, this one gets complicated. We actually have to split over the D block, and I'll get to that in a moment. But zinc readily makes 2+ because we go back 2 spaces and we get to the noble gases. Okay? So that's pretty cool. All right? So now there are a few exceptions here that we're going to go through. So we remember the Aufbau principle. Electrons are added one at a time to each successive orbital. Okay? There's Hund's rule. I haven't introduced this yet, but I will now. So Hund's rule says the lowest energy configuration, and lowest energy means most stable, and the most stable means that's what you would observe in nature. So often in nature, the most stable thing that we see is the lowest energy. Okay? So the lowest energy configuration for an atom is having the maximum number of unpaired. So if we can break the Aufbau principle rule just slightly to have the maximum number of unpaired electrons, that will happen, and that creates an exception. Okay? Another exception to the rule, half-filled orbitals are more stable than partially filled. Okay? So there's a couple things we have to remember. Unpaired electrons, if we can do it, they want to be unpaired. But if we can also make a half-filled orbital, half-filled orbitals are extremely stable because in a half-filled orbital, all the electron arrows are pointing in the same direction. And so it gives a consistent magnetic moment. It makes it really stable. Okay? So there's just a couple examples of these that I'm going to make you remember. And so here they are, chromium and copper. So let's talk about chromium and copper. Let's first talk about what we would expect for chromium. So as it turns out, chromium with 24 electrons, I'm just going to write down the electron configuration in the easiest way I know how, which first I find chromium, there it is, okay? And now I go backwards and find its noble gas that it's closest to, which is argon. I don't go forwards, I go backwards. So argon, so I can write down argon. And now as I move forward, that's 4s2, okay? So argon, 4s2, and then now 3d, 1, 2, 3, 4. 4s2, 3d4. So I could count all the way through, right? I could say 1s1, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d, 1, 2, 3, 4. However, it's much easier to just write argon, and then after that, 4s2, 3d4. So this is what you would expect, and let's put all of that in. Okay, so I'm just going to populate all of this. And I've got to go all the way up to the, oops, I put 3D4, yes. So 4s2, 1, 2, and then 3d4. 1, 2, 3, 4. So this is what you would expect to happen. Okay? But that's not actually what happens. So what happens? Well, what happens is because the 4s and the 3d are so close in energy, right? If you think about this graph here, this graph is physically accurate. So the 4s and the 3d levels are very, very close. And as it turns out, what you can do now with these 24 electrons, you still have to have 24, okay? So that 4s2 is paired up, but look, there was an open space over here. So now that 4s paired electron jumps over to here and says, haha, I've got more room to spread out over there. So what actually happens is this becomes argon 4s1 3d5. Okay, so this is what you actually observe because now we have two half-filled orbitals, right? 4s is half-filled and 3d is half-filled. So that becomes extraordinarily stable. And so not only does this happen with chromium, but it also happens with molybdenum and tungsten, right? So this is part of the periodic trends. If we notice that molybdenum, it will also be in that D4 position. Tungsten will also be in that D4 position. Okay? So all of those things, I want you to know that chromium, molybdenum, and tungsten, all in the D4 position, 1, 2, 3, 4, they can become half-filled, two half-filled orbitals. And so this is what their configuration ends up being, 4s1, 3d5. Okay? And it's also why chromium can often have the oxidation states that it has. So we noted that the transition metals can often have variable oxidation states. Like, for example, sometimes iron can be +2, sometimes iron can be +3. That's because of all of this complication. Because there's so many different rearrangements of the electron configuration, the transition metals are a mess. They can have loads of exceptions, which is why you see sometimes iron is +2, sometimes iron is +3, sometimes chromium is +7, sometimes chromium is +3. So there's all kinds of things that we can explain that we observe in nature because of these oxidation states, or really because of these electron configurations. Okay, so now what about copper? So copper is another exception I want you to know. 29 electrons. That's a lot of electrons. Let me find my cheater note so I get it right here. Okay, so copper with 29 electrons. If we find copper, let's see, there it is. So the easiest way to get that configuration is to go backwards and find the noble gas. So there's argon, okay? So I would say argon, and then now 4s2, and then my next block is 3d, and that becomes 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. 4s2, 3d9 is what you would expect. However, okay, and so let's fill that out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. I still got a bunch to go. 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29 of those things. Oh my goodness. Okay, so this is what you would expect. But it's not what happens, okay? And what ends up happening with this particular orbital, with copper, okay, as it turns out, the 3d and the 4s energy levels end up switching in energy. And they end up switching in energy because this becomes very stable with the fully populated shell, okay? Or subshell, nearly fully populated. So what ends up happening with this is now you get a 4s1 and a 3d10. So what you actually observe is the following. Argon, and it actually becomes 3d10 first and then 4s1. This is a tricky example, okay? And that's what makes it an exception. I mean, chemistry is like the science of exceptions, okay? And so, as you might guess, the same thing that happens with copper copper, silver, and gold. Silver and gold do the same thing due to the periodic trends, okay? So I just want you to know these two examples for chromium and copper, and also understand that it's observed in molybdenum and tungsten, not so much with Seaborg, with SG, Seaborgium. And also, if you notice here, under gold is one of our fictitious, like man-made elements that's not very stable in general. So just know chromium, molybdenum, and tungsten, and copper, silver, and gold have this unexpected result. Okay? And so the last thing that I'm going to say about electron configurations is this competition between potential energy and kinetic energy with the core electrons and what we call the valence electrons. And I want you to know about these valence electrons. Okay, this is really important. So the valence electrons make up the top unfilled level. Or in case of the noble gases, it will be filled. So for example, here's carbon. Okay, carbon's core electrons are 1s2. So these core electrons, we really think of these as buried. They're deep down in the core of the atom, which means they have the smallest potential. So like they're the closest to the ground, right? So they have the smallest potential. But that means they have the highest kinetic energy to remove. So that means these core electrons are very difficult to remove, okay? So because of this small potential and high kinetic, core electrons are difficult to remove. And so what that means is we don't do a lot of chemistry with core electrons. Don't do much chemistry. They're buried. They're really hard to get to. They are shielded, or rather, excuse me, the valence electrons are shielded. So let's get to that next one, okay? So now with the valence electrons, and for any atom, the valence electrons make up whatever its row is, okay? So for example, carbon is 2s2, 2p2 valence electrons. Nitrogen would be 2s2, 2p3. Oxygen would be 2s2, 2p4. But now what about calcium? Okay, so calcium's valence electrons are 1s, 2s, 3s. So calcium only has 4s valence electrons. So it's whatever that last row is makes up the valence electrons. This is where chemistry happens. Chemistry happens with the valence electrons, okay? Because for one, they're in these open shells. They're not closed up. But two, they are shielded from the positive nuclear charge by the core electrons, okay? So there's the nucleus right here, very, very close to the core electrons. That positive, nucleus is really attaching itself to the negative electrons very strong, okay? So the valence electrons get shielded. They get blocked by that. And the result is the valence electrons are really easy to remove. It's the valence electrons that are getting exchanged in a redox reaction, for example. So when we talk about oxidation as loss, reduction as gain, that's happening with the valence electrons. As we will also see when we make molecules, so when we bond atoms together, we bond them together via their valence electrons, okay? And they are called valence because there is a vacancy in the orbitals. That's where it comes from. There is a vacancy in these orbitals. So they are valent. They make up the valent orbitals, okay? So let's see here. I think that's where I'm going to end it for this lecture, and it'll just be one more short lecture on periodic trends. Okay, so let's take a look at the learning goals here. So we came up with know how to draw an orbital energy level diagram, how to populate it with electrons, and then how to come up with electron configuration using Aufbau, Hund's rule for any atom or ion, and know the exceptions in the class. So this is a huge learning goal. It took me a whole lecture just to do it. So make sure that you feel okay with that. Okay, folks, one more short video for chapter 7.